Hello, you're welcome back. All right, so now we are going to be looking at the very first topic that you need to study in physics, and that's measurement. All right, now measurement is really very important. Why? Because every practical procedures you ever undertake requires measurement. Okay, there's no way you undertake practicals in physics without taking measurements. All right. So now, of course, what's measurement? In measurement, what we do is that we find the size. Okay, we find the size of a physical quantity. So we basically find the size of a physical quantity. Now the question is, what's a physical quantity? All right, any quantity that can be measured. Any quantity that can be measured is actually a physical quantity. All right, for example, length can be measured, mass can be measured. Okay, time also is a quantity can be measured. It's a physical quantity. Now, this physical quantities in physics is divided into three. All right, we have what we know as the fundamental physical quantities. Then we have the derived physical quantity. Then we now have category known as the vectors. Category called vectors and scalars. All right, but in this tutorial we are just going to treat fundamental and the derived quantity. As for the vectors and the scalars, we're going to treat them as a topic. All right, let's start with a fundamental physical quantity. And of course, as the name implies, they are fundamental. All right, fundamental physical quantity are fundamental. Why? Because they provide the basic unit of measurement. Okay, they provide the basic. Okay, so invariably, you can simply say that they form the foundation of all measurement. Okay, so they form the foundation in which all other quantities known as derived quantities get their definition from them. All right, they are fundamental, and that is why you need to know all the fundamental physical quantities in physics. All right, why? Because any formula you ever encounter in physics, if you trace it back, you understand, you will always trace it back to the fundamental quantities. So I'm going to list them out. There are 7 of them. All right. Number 1, you have the mass. Let me represent that with M. Have the length. That's L. Number 2, have the time. Of course, I use T. Small letter T for now. All right. We also have the quantity called electric current. Is fundamental. And of course, the symbol I. Okay. Next we have temperature. Okay. In most cases we use theta, or you can use any symbol. All right. Have luminous luminous intensity. luminous intensity. Alright, and I should do for that. Then of course 7, the last but not the least, amount of a substance. Amount of a substance. A. Alright, so these quantities are fundamental physical quantities. They form the foundation of all measurement in physics. Now let's proceed to the derived quantities. Derived. Of course, as the name implies, okay, they're all derived, okay. They are derived, gotten from the fundamental quantities, gotten from 1, 2 or more, okay, gotten from combining 2 or more fundamental quantities in a formula, okay. So when you combine 2 or more fundamental quantities to create a formula, then such formula is called a derived quantity. We are going to be looking at some examples. The very first example I'm going to look at is speed. Speed is a derived quantity derived from distance all divided by time. And of course, you know very well that distance is measured in length. Distance between these 2 points is the line between those 2 points, then time, small letter t. Okay? Velocity is the same, is displacement all over time, but let me get to acceleration. Or better still, let me still put that down. Velocity is displacement divided by time. Displacement between 2 points is also measured by the length between those 2 points, all right? But the difference is that velocity displacement is a vector quantity. It has direction, while speed is a scalar quantity. It doesn't have any direction, but it's still measured in length, all right? Then of course number 3, I have acceleration. Okay, acceleration is simply velocity all over time. We already know that velocity is length all over time, then divided by time again, so that will give us length all over t square, length all over time square. All right, so force is also a derived quantity, because force is derived from mass times acceleration. There's still another. We have work. Work done is always given as force, then times distance. It's a derived quantity. Okay, I can go on and on. I can also talk about power to be equal to the work done divided by time. So which simply means that all the formula you can ever remember in physics are mostly derived. Okay, so I hope that is well understood. All right, now we'll discuss a very important term known as dimension of a quantity, dimension of a derived quantity. Okay, the dimension of a derived quantity is simply the derived is a derived quantity that is expressed as exponential product of the fundamental quantity, okay, using the symbols of the fundamental quantity. All right, if that doesn't actually make sense, I will just tell you what I mean. If I want to express a derived quantity in dimension, okay, if that derived quantity has mass, I'll use capital letter M to represent that, okay. If that derived quantity has length, I'll use capital letter L to represent that. If that derived quantity has time, I'll use capital letter T to represent that, okay, etc. So on and so forth. Then my answer, okay, then the formula I will write using this symbol, okay, is expressed. I will express it in an exponential form. That means I will not, okay, keep my answer in fraction, but I have to express it in an exponential form. So that I will know the power of both the M, the L, and the T. Okay, I think example will do. Okay, let's say you are being asked to express the following formula in dimension, okay? Let's express the formula that we already know, the derived quantities we know in dimension. Let's start with velocity. If you are being asked to express velocity in dimension, simple, you know velocity is equal to displacement all over time, which of course is length all over time, right? Length in dimension, we use capital letter L to represent that, then time, capital letter T. I can't keep my answer this way, okay? I will express it in exponential form. How do I do that? I'll find the reciprocal of T. I have to take T to the, okay, to the numerator. I have to move it. And once I move T, it becomes T raised to the power minus 1, right? In indices. That's very correct, okay, according to law of indices. Of course, exponent is something as power, okay? Number 2, acceleration. If you are being asked to express acceleration in dimension, don't forget that acceleration is velocity divided by time. Velocity I have expressed in dimension. I'm having L T raised to the power minus 1. Then time again, capital letter T. Move this, you know what I will get, okay? So if I move that, if I find the reciprocal of that T, I'm gonna have T raised to the power minus 1 already here. Then times, I move this one up, becomes T raised to the power minus 1. Of course, in indices, T raised to the power minus 1 times T raised to the power minus 1, okay? I will have, of course, the power is minus 1, which is minus 2. So I'm having T, L T raised to the power minus 2. That is acceleration. Number 3, force. If you're expressing force, we know already that force is equal to mass times acceleration, okay? Mass, capital letter M. Acceleration, we've done that. Lt raised to the power minus 2. As simple as that. Number 4, work. If you are to express work, you know that work is force multiplied by distance. All right, force already is ml t raised power minus 2 times distance, which of course is still length L. So in this case, L times L will give me L square. So work, the dimension of work is ml square, then t raised to the power of minus 2. Number 5, power. If I'm to express this, so I have to write the formula first. You know very well that power is work divided by time, and work is ml square t raised to the power of minus 2, then divided by t. Okay, what does that actually mean? It simply means that my answer is gonna be ml square t raised to the power of minus 2, then times t raised to the power of minus 1. So this is gonna be equal to ml square, then t raised to the power minus 2 minus 1, that is minus 3. Okay, so you can actually express any formula in that, in as much as you know the formula. Okay, you can express them in their dimension. All right, so I hope that is well understood. So we are going to be looking at units. We've talked about quantities, okay, derived and fundamental quantities. So we're going to talk about the unit of measurement in the next video. All right, see you in the next video. Thank you very much.